course, drawing electrons as dots is like hugely simplifying things, because we just got done talking about how electrons are waves and particles at the same time, and there's all very, very complicated. And now all of a sudden they're just dots on a piece of paper. So it's not that simple. So we've been talking about sharing electrons. Well, the electrons are not always shared equally. Sometimes we have unequal sharing. So if you think about sharing a bed with someone, whether that's a spouse or a sister or just someone you like a lot, I don't know, there's blankets involved, right? And it always happens, there's one person that tends to take the blankets from the other person, right? You guys are smiling, you know this happens. So that's kind of what this unequal sharing is like. If we look at hydrogen and fluorine, fluorine is a blanket hog. So there's a pair of electrons being shared between the hydrogen and the fluorine, but fluorine is grabbing more of them. So we've illustrated that here. This is the fluorine atom and the hydrogen atom, and what we've got here is electron density, and we see that the electron density is more over towards the fluorine side than the hydrogen side. So this unequal sharing ends up being an unequal distribution of charge. And so the hydrogen end of this molecule is going to be a little bit positive, and the fluorine end is going to be a little bit negative. It's not an ionic bond. The electron has not been transferred from hydrogen to fluorine. They're sharing it, but just not very fairly. And so because the electron is spending more time over here, this end of the molecule is going to be a little bit negative. So this funny little squiggle is a Greek lowercase delta. It looks like maybe a lowercase d with a postured problem. What that means is a partial charge. So this isn't -1. It could be minus 0.3 or minus 0.02. I mean, it's part of a charge. And this would be the equal amount, but positive. And we can observe this unequal sharing by putting these hydrogen fluoride molecules in an electric field. So normally these molecules would just be kind of randomly distributed. You turn on the electric field, make this side negative and this plate positive. Pointer went away. And the negative side of the molecule is attracted to the positive plate. The positive side is attracted to the negative plate, and it's just kind of crazy. They all just line up, like stand at attention. We're all going to face the same direction and be organized. And that's because there's unequal sharing. So we call this a polar covalent bond. If you think about the North Pole and the South Pole, they're opposite ends of a sphere, right? But there's this magnetic field, and one end at the North Pole and the other end at the South Pole. So polar means a separation of things, right? So this is a polar molecule. That bond is called a polar covalent bond. It's between an ionic bond and a pure covalent bond where the electrons are being shared equally. Make sense? So why does fluorine hog the blankets? Why does it take the electrons? It has to do with electronegativity. And that's defined as the ability of an atom to attract electrons to itself in a chemical bond. So how strongly can it steal the blankets? This is inversely related to atomic size. So smaller atoms tend to be more electronegative, and larger atoms tend to be less electronegative. Fluorine is the most electronegative element. The noble gases don't really form bonds. I mean, you can force them to form bonds, but we just don't run into compounds unless we're intentionally making them. So we just leave the noble gases completely out of our discussion of electronegativity. So here's a kind of a cool chart of trends in electronegativity. So as we go across a period, we see that electronegativity in general goes up, and as we go down a group, electronegativity decreases. So that is opposite to atomic size. Really, the best way to remember trends for electronegativity is fluorine is the most electronegative, and so if you get closer to fluorine, electronegativity increases. So it's like a hill, and you're just kind of going up the hill, and fluorine's at the top. So we can look at specific electronegativity values, and we need to talk about that, but in practice we're not going to really do that very much. So if you look closely here, nitrogen has an electronegativity of 3.0, and chlorine has an electronegativity of 3.0. And just looking at trends, you would not necessarily predict that those are the same. And there's other pairs like carbon and sulfur and iodine are the same. So those do exist. So bond polarity, we're talking about how equally or unequally are the electrons shared. And how polar a bond is depends on the difference in the electronegativity. So these divisions are arbitrary. It's a continuum here, but we kind of have to just draw a line somewhere, right? It's like, when does a person become an adult? Well, it kind of varies for different people, right? But generally in this country, we say when you're 18, then we'll let you vote and do all kinds of other things, but we won't let you drink yet. So it's kind of arbitrary. So here's a pure covalent bond. The book uses the word pure. I prefer the word nonpolar because it's more descriptive. Nonpolar bond, electrons are shared equally, and we say, well, that's if the difference in electronegativity is 0 or up to 0.4. So it's just a little bit different. We'll call that a nonpolar bond. In the middle here, from a difference of 0.4 up to a difference of 2, we're going to say this is a polar bond. There's going to be definitely a positive and negative end to this molecule. And if the difference is over 2, we're going to say this is an ionic bond. The electron's actually getting transferred. I'm going to go back here a minute because I didn't give you one of my favorite analogies, and I didn't talk about this arrow thing. So I've told you before, I think of electrons as being a lot like little boys. They remind me of my son Andrew, a bit unpredictable, kind of out there, right? So in my analogy, hydrogen is one home and fluorine is another home, and those two electrons in that bond, one boy from each home, and they're playing together. Now, if the homes are the same, like if we have hydrogen and a hydrogen, this house, they've got a black and white TV, an old Thomas the Tank Engine VHS tapes, and this one has the same thing. The boys are going to spend equal time. One house is not more attractive to them than the other. But here we have hydrogen again and fluorine is the coolest house on the block, right? Big screen TV, all the different satellite channels. They've got every game system known to man. They have a soda fountain in the kitchen, trampoline and a swimming pool with a slide and a diving board. I mean, this place is awesome, right? So those two little boys, one from hydrogen's very boring house and one from fluorine's really cool house, where are they going to play most of the time? They're going to play at fluorine's house, right? Why? It's more attractive. Fluorine has more attraction for those shared electrons than hydrogen does. So what's up with this arrow thing? So we can use the delta plus and delta minus to indicate which end of this bond is positive or negative. We can also use an arrow. The arrow points to the more electronegative atom, and then we put a little plus sign here to show that we're not just drawing arrows. This means we're indicating the polarity of the bond. This side's positive, that side's negative. So I think of that arrow a little bit as mom's out working in the garden, and Dad comes home and he's like, "Where are the boys?" And she points, "They're over there." Right? So the arrow is pointing to the cool place where the electrons are spending most of their time. I don't know why I like that analogy so much, but I do. So of course, we've got something like this. We're going to measure it, right? So dipole moment is a way to measure the polarity of a bond. We get a dipole moment occurring anytime there's separation of charge. So dipole moments can happen in different contexts. They use the letter mu to represent the dipole moment. So the dipole moment is equal to the charge magnitude times r, which is the distance. So I'm telling you about this. We're not actually going to do any calculations with that. You just need to have heard about it. Okay? A common unit of dipole moment is the debye. And a debye is 3.34 times 10 to the minus 29 coulombs times meters. So Q is charge measured in coulombs, and R is a distance measured in meters. And so that gives us this weird unit. So here's a table showing some different molecules, and we can look at the difference in electronegativity between the two elements, and we can also look at the dipole moment. So a chlorine molecule, we have two identical atoms. Is one going to be more attractive to the electrons than the other? No. So there's going to be perfect equal sharing between those two atoms. The difference in electronegativity is 0. The dipole moment is 0. There's no separation. If we look at a chlorine fluoride molecule, so there's a difference in electronegativity of 1. The fluorine is more attractive to the electrons than the chlorine. So there's some separation of charge here. The dipole moment is 0.88. Now, you can't just predict that because it depends on the difference in electronegativity, but also in the distance between the two atoms. So that's something that just gets measured. And that's why we're just not going to pay too much attention to it after this slide. HF, we looked at that one. Here's the difference is 1.9. So bigger difference in electronegativity, larger dipole moment. Lithium fluoride, difference of 3.0. Now this is considered an ionic compound because the difference in electronegativity is greater than 2. And the dipole moment, 6.3, much higher. We can also look at percent ionic character, which would be the ratio of the dipole, of the bond's actual dipole moment to the dipole moment that would be there if the electron was transferred. So we talk about ionic bonds as being a transfer of electrons. The sodium gives an electron to the chlorine and they're separate and they're done. That's not actually how it is. So no bond is 100% ionic. It's not that that electron really gets completely transferred, it just gets mostly transferred. So if we look at this, we're looking at percent ionic character on the y-axis and difference in electronegativity on the x-axis. And so we see clusters. So we've got this clump of compounds down here with less than 25% ionic character, and they've got small electronegativity differences. Up here, we have another cluster of compounds. 50% ionic character is what we consider the dividing line between ionic and covalent or molecular. So here's HF hanging out here. We also looked at a difference of 2.0 as being the dividing line between ionic and molecular. And so HF is really close to these borders, but it's not ionic. The rest of these, if you look at them, they're all metal, non-metal, right? We learned earlier to identify something as ionic if it had a metal and non-metal in it. HF, 2 nonmetals. Chapter 3 says that's a molecular compound. It is a molecular compound. So we can still rely on those earlier ways of identifying molecules, But this is just showing that there's more underneath that. Any questions about that? So it's more complicated than that, and yet we can still just stick with our simple descriptions. So we need to be able to answer questions like this, and these sorts of things. This is something that will be important in OChem. Being able to identify whether you've got a polar bond or a nonpolar bond. Is this ionic? So we've talked about percent ionic character, and we've talked about differences in electronegativity. And I'm going to give you some shortcut kind of rule of thumb things that work almost all the time and don't involve any math at all. Okay, so this is my short list. Let me just double check. No, I don't have it written down anywhere. That would be too easy. I really should do that one of these days. Okay, so 2 atoms of the same element. Could that possibly have a difference in electronegativity? No. So if you have 2 atoms of the same element, always nonpolar. That one's always true. What if you have 1 metal and nonmetals? You could have just 1, or you could have more than 1. Non-metals. Non-mentals. So you got a metal and 1 or more nonmetals. What kind of a compound is that? It's ionic. We learned to identify it that way. That's going to be always ionic. Now that doesn't mean that the electron is really completely transferred, but it's over 50% ionic character, and that's good enough. So what if you have 2 different nonmetals? Well, we learned that 2 nonmetals forming a compound, that's going to be a molecular compound, right? So this is always covalent. But the question is it polar covalent or nonpolar covalent? Most of the time, it's polar covalent. Mostly polar. There are exceptions. I pointed out a couple of those. I think it was carbon and iodine, nitrogen and chlorine, something like that. They had the same electronegativity. Those would be nonpolar bonds. There are others where the difference is 0.4 or less, and those are nonpolar bonds. There's only one situation that's an exception to this of being polar that I want you to remember, and that's a carbon-hydrogen bond. Carbon-hydrogen bonds are nonpolar because the difference in electronegativity is small enough that they're nonpolar. Okay? So when we look at a question like this, I want you to use these just kind of guidelines. I'm not gonna give you a chart of electronegativities on the next exam. That's just too much work. We don't need to do that. What we need to be able to do is just look at the periodic table and most of the time be right in saying it's polar or nonpolar. So when we look at a bond between iodine and iodine, is that going to be, and I'm going to get rid of, oops, don't want to do that. We're going to call this nonpolar. Is it going to be a nonpolar covalent bond, a polar covalent bond, or an ionic bond? Nonpolar. That's this category. 2 atoms of the same element. So this is a nonpolar covalent bond. How about cesium and bromine? Ionic, because cesium's a metal, bromine is not a metal. So this one's ionic. How about phosphorus and oxygen? Polar covalent. We can't know for absolute sure, but we're going to say that's polar covalent. You want to look it up?
No.
No, we don't want to look it up. That's too much work, right? Most of the time, that's going to be right. And the few times that it isn't, we'll know more about it, and it won't matter. The one exception, though, that you need to be aware of is carbon-hydrogen. Carbon-hydrogen bonds are nonpolar. Any questions?